Hello everybody, welcome to this lecture on the course of computer aided power system analysis. In the last lecture we have looked into the aspect of bad data detection. We have looked into the entire procedure with an example, but there one particular issue we did not explain in detail. So, let us look at that detail today first, and then we will after that we will talk about the issue of power system state estimation, which is the basic purpose of this entire unit. So, what we are doing is that bad data detection, when we are doing bad data detection, what we did is that we calculate a fact and if f hat is greater than c k alpha, then we said that bad data exists. Then we say that bad data exists. Now, to find out that which one is the bad data, now to find out which one is the bad data, we did what we did is we calculated some quantity called zi minus zi hat by rii dash root. We call it as standardized error, and then we said that whichever measurement has got this error to be maximum, that is basically the maximum magnitude. So, that particular measurement is actually taken to be a bad data, and then we simply discard it and then we again do it. Now, the question is that what is the justification for calculating this? Now, to do this, what we calculate, please note that when we said we have calculated expected value of zi minus zi hat by square by rii dash, we said that it is equal to 1. So, this can be written as simply zi by zi minus zi hat by root over rii dash whole square is equal to 1. That can be said. Now, suppose now we also note that ei hat, that is the estimated value of error, is zi minus zi hat. So, this also we know, this is the estimated error. Now, if we do define one random variable, now please note that this is a random variable. Now, if I do define one random variable such that which is, let us say ei hat minus 0 by rii dash. So, this is nothing but zi minus zi hat by rii, sorry, root over. So, now this random variable has got the property that this has got a variance is equal to 1. So, then therefore, this quantity is nothing but the standardized error with a mean is equal to 0 and the variance is equal to 1. So, then therefore, that is why we call this quantity to be the standardized error, and so then therefore, we first calculate this particular standardized error and then we simply take the absolute magnitude of the standardized error and then we reject that particular measurement which has got the absolute maximum value of the standardized error. Now, one important point needs to be understood. Suppose I do have m is the number of measurement, and n is the number of states. Now, in case now suppose that we first do an exercise of the state estimation and then we do the cross check that whether any bad data exists or not. If any bad data exists, so then what happens that we simply discard that particular measurement. So, when we discard that particular measurement, so then in that case my effective number of measurement which we use becomes m minus 1. For example, in our example which we have shown in the last lecture, that earlier m was 4, and n is equal to 2, but when the fourth measurement was detected to be a bad one. So, then we have simply neglected or rather discarded that particular measurement, and then again we have done the state estimation using m is equal to 3 number of measurements. So, then therefore, total number of measurement utilized has reduced by 1. Now, here in this example we have found that well when we have taken let us say 3 measurements, we have got our estimated states to be acceptable, because in that case we did not detect any kind of bad data. But it may happen that in a system there are multiple meters which have gone bad. Say for example, say let there are multiple let there are L meters which have got L meters which have gone bad, So, then what happens? We start with this m meters, then we first detect 1 meter, that is basically which is got the highest value of the standardized error. Then we simply discard it. So, then after that my total number of effective measurements becomes m minus 1. Again when we do our state estimation using this m minus 1 measurements, again we find out the next meter which is bad. So, then after that my effective number of measurements become m minus 2. So, if we do so then therefore, if we do follow this process, ultimately my effective number of measurements will be m minus L. Now, if my effective number of measurements m minus L becomes less than n, so then in that case this state estimation problem would be an indeterminate one, because the number of equations available is less than number of states to be estimated. So, then therefore, to cross check or therefore, to take into account the possibility of existence of bad data, what happens is that we usually take number of measurement to be reasonably large as compared to the number of states to be estimated. So, then therefore, the one of the most important conclusion is that for any state estimation exercise, the number of measurement is always taken to be reasonably large as compared to the number of states to be estimated. So, we always say that m is always greater than m, it is always greater than n. So, that is the very important conclusion. So, this completes the discussion of the basic theory of the state estimation, and we have explained this basic theory of state estimation by taking a very simple DC circuit. But our objective, as we have stated in our initial lecture of this module on state estimation, our objective is to ultimately to monitor the power system, monitor the transmission or distribution grid. So, then therefore, we need to discuss about the power system state estimation. So, then now in the case of power system state estimation, what happens? So, now our discussion is, now we start our discussion on power system state estimation. Many of this or rather most of this discussion will follow the discussions whichever we have done, but we have to add something to take into account the basic nature of the power system equations. Now, first thing, that what are the states? So, for any transmission and distribution grid, the first thing, what are the states? Now, let that there are n number of buses, there are n number of buses, n capital N number of buses, let capital N number of buses. Now, at each bus, now we have already explained when we have discussed about the load flow analysis, we have already explained that if we know V I and theta I, V I and theta I for all I is equal to 1 to n, so then we would be able to calculate everything else in the system. So, then therefore, it follows that when you are talking about estimating the states of any power system, we can take V I and theta I for all the buses to be the states. So, then therefore, it follows that it appears that we have got total number of states n is equal to 2 into n, because at each bus we have got voltage magnitude and one angle. But then, as we have also said in the when we have discussed about power system state estimation, that for measuring any angle or rather for calculating the value of any angle, we need a reference value of angle, because without any reference value no calculated value of angle does not make any sense. So, then therefore, we have to make one value of angle to be equal to 0, and once we make one value of angle is equal to 0, rest of the other angles would be calculated with respect to this particular angle. So, then because we are making one value of angle to be 0, usually we make it, let us say, at bus number 1 or let us say at let us say a slack bus, but the central point is that we do make one angle to be equal to 0. So, then therefore, total number of states is equal to 2 n minus 1. So, and these states are these states are given by theta vector, that is theta 2, theta 3 up to theta n transpose. So, this is an n minus 1 cross 1 vector. Here we assume that theta 1 is equal to 0 and v vector, that is v 1, v 2 up to v n. So, this is n cross 1 vector, right. We take theta 1 is equal to 0. So, this is n minus 1, this is n. So, that we have got total number of states is, so we write that this is the total number of states. So, total number of states, this is the total number of states to be estimated. So, now this is the basically the total number of states to be estimated. So, now we need m number of measurements where m is greater than n. So, now let us look at that what could be the possible measurements. So, for that let us say look at some simple system, just a 4 bus system, just a 4 bus system, just a 4 bus system. So, these are all buses, these are all buses. So, as far as a measurement is concerned, we can let us say this is bus 1, bus 2, bus 3, bus 4. So, as far as this measurement is concerned, we can think of that we are measuring let us say P 1 2, Q 1 2, right. We can also measure, let us say, P14, Q14. We can also here can measure I14, that is the magnitude, or in other words we can measure all real power flow over all the lines, we can measure all reactive power flow over all the lines, we can also measure the current flow magnitude over all the lines. We can also measure some of the voltage magnitudes, right. Of course, we probably cannot measure the angles, but we can always measure the sum of the voltage magnitudes by just putting a voltmeters. So, then therefore, our possible number of measurements, or rather the possible measurements are, so our possible measurements are possible measurements are Pij, Qij, cap Iij, Vi. What is Pij? Pij is the real power flow over line Ij. Pi is the real power flow over line Ij. This is the reactive power flow over line Ij. This is the magnitude of current flow over line Ij. We can also measure possibly Pi Qi, that injected power at some bus P and injected real and reactive power at some bus I. I mean, how is it possible? For example, just for example, suppose that I do have a load here, and this has got PQ load, and if I do put a, let us say, an wattmeter kind of a thing. So, then therefore, we would be able to measure that what is the amount of load, and so then therefore, our measured value of Pi and Qi would be nothing but the negative of these measurements. Similarly, if I do have an let us say generator here, I can always put another wattmeter here, and then we can always measure that what is the value of Pi and Qi from this particular generator. So, then therefore, our possible set of measurements can be anything. Now, if we look at, if we do recollect our earlier discussion, in our earlier discussion when we have discussed about the state estimation using a simple DC circuit, we have noticed that the measurement vector Z is given by some constant matrix X plus some vector E. Please note that this is a constant matrix, and why this was a constant matrix? Because all these equations were linear equations, and of course, these equations were linear equations because of the simple fact that we have taken a very simple DC circuit, and in any DC circuit any measured quantity can be expressed as a linear combination of the unknown states. But what happens in the case of power system state estimation? For example, if we look at the expressions of Pi and Qi. So, Pi I know that it is simply k is equal to 1 to n Vi Vk Yik cos theta I minus theta k minus alpha Ik. Similarly, Qi is also k is equal to 1 to n Vi Vk Yik sin theta I minus theta k minus alpha Ik, right. Now obviously these two equations are nonlinear in nature. So these two equations are nonlinear in nature. So these two equations are nonlinear functions. Right. Now these two equations I can say that as if that pi can be said that as if that it is a function of pi of vector vi, v and theta. Similarly qi is can be said as a function of v and theta, and these are nonlinear functions. Similarly, if we do write down the expression of Pij, Qij and Iij, that is basically the magnitude of Iij, we will find that these expressions are also nonlinear functions of the unknown state vector v and theta. So, we note that in general in power system state estimation, in power system state estimation the measured quantities are, this we must, so this is a very important observation, the measured quantities are nonlinear functions of the state variables. So, this is a very important to understand that these are nonlinear functions of the state variables. Now, let I denote my x vector x as v transpose theta transpose t. Please note that there is too many transpose, but what happens is that v transpose is actually, just to explain it, v transpose is actually v1, v2, vn, and theta transpose is actually theta 2, theta 3, theta n. So, then therefore, v transpose theta transpose theta transpose is nothing but v1, v2, vn, then theta 2, theta 3, theta n, right. So, then when I take v transpose theta transpose of, so then transpose of this transpose, we get that v1, v2, vn, theta 2, theta 3, theta n transpose. So, we simply make it as a column vector. So, then therefore, x is a column vector. So, we say that x is a column vector, x is a column vector and the dimension is 2n minus 1 cross 1. Now, suppose I do have total number of measurements as m. So, my measurements are z I. Now, let us say the measurements are, let us say the measurements are, let us say z I for all I is equal to 1 to m, right. And these measurements can be either Pij or Qij or magnitude of current Iij or Vi or Pi or Qi, anything, they can be anything. Only thing is that m is greater than n. So, that is the most important thing we said, and this is due to this fact that we are making this constraint to ensure that if there is any bad data which can be detected and removed. So, then therefore, because these are all nonlinear functions, so then in general we can write down that h I, in general I can write down that z 1, that is the measured value z 1 is some function h 1 of x plus E 1, z 2 is some function of h 2 of x plus E 2 dot 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 z m is equal to some function of plus E m, where h 1 h 2 dot 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 h m are nonlinear functions of x vector x. Now, let we say that x vector is given by x 1 x 2 dot 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 x n transpose t. Of course, we note that, of course, we always should note that n is equal to 2 into capital N minus 1, that we always note, but x 1 x 2 is equal to n. So, then therefore, these equations can be written as z 1 is equal to h 1 of x 1 x 2 x n plus E 1, z 2 is equal to h 2 function x 1 x 2 up to x n plus E 2 dot 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 z m is equal to h m into x 1 x 2 into x up to x m plus E m. So, this is the general measurement model. So, this is the general measurement model, general measurement model for power system state estimation. So, this is the general measurement model. So, and we note that in this general measurement model all these functions are basically nonlinear in nature. So, then therefore, the technique whatever we have used earlier cannot be applied immediately directly. So, then in the in the next lecture we will look at that how this nonlinear functions can be incorporated into our general state estimation process which we have discussed earlier. Thank you.